Welcome to ArcTech AI Institute. Today, we unravel diffusion models, a revolutionary class of generative AI. They are setting new benchmarks in high-quality, diverse data synthesis. This is the dataset for our denoising model. The reverse process is where the magic of generation happens. A powerful neural network learns to predict and remove the noise from a given noisy image, gradually reconstructing the original data. Reversing a stochastic process is incredibly challenging. The neural network must learn the subtle, nonlinear conditional probabilities that govern the denoising step. The neural network, often a UNet, is trained to predict the noise component epsilon that was originally added to x0 to produce xt. This prediction is central to the denoising. The model then iteratively applies its learned denoising step over hundreds or thousands of time steps, gradually refining the image. The network effectively learns the reverse conditional probability distribution, how to infer xxt-1, a slightly less noisy version, from the current noisy state xt. Predicting the noise, epsilon, is deeply connected to estimating the score function of the data distribution, which is the gradient of its log probability density. This unification is foundational. The seminal DDPM paper demonstrated that a simple objective, training the network to predict epsilon, is remarkably effective for high-quality generative synthesis. To generate, we begin with a randomly sampled pure Gaussian image, xt. The trained network then iteratively denoises it, step by step, until x0, our generated image, emerges. Diffusion models excel at conditional generation. By integrating information like text embeddings or class labels, we can guide the generation process to produce specific outputs, like a dog playing in a park. Unlike GANs or VAEs, diffusion models operate on a unique principle. They iteratively add noise to data, then learn to reverse this degradation process. This allows them to generate novel samples from pure noise. Witness the transformation. From amorphous noise, a high-fidelity image gradually crystallizes, demonstrating the network's mastery in reversing the forward entropy. The UNet architecture is the workhorse behind the noise prediction in most diffusion models. Its design is exceptionally well-suited for pixel-level prediction tasks. The encoder path of the UNet progressively downsamples the input noisy image, extracting increasingly abstract and high-level features at lower spatial resolutions. The decoder path then upsamples these features, reconstructing the image back to its original resolution, informed by the learned semantic context from the bottleneck. Skip connections are crucial. They directly pass fine-grained spatial information from early encoder layers to corresponding decoder layers, preventing loss of detail during upsampling. Beyond the noisy image, the UNet also receives the current time step t as an input. This time embedding informs the network about how much noise is present, guiding its denoising efforts. Thus, the UNet's full input is a noisy image and its current time step. Its output is the predicted noise component, epsilon, which is then used to denoise the image. Score-based generative models represent another powerful family closely related to diffusion. They explicitly train a neural network to estimate the score function of data distributions. The score function is mathematically defined as the gradient of the log probability density function, delta log p of x. It essentially points in the direction of increasing data likelihood. Sampling from score-based models often employs Langevin dynamics. This iterative process takes small steps guided by the estimated score function, gradually refining a random sample into a coherent data point. At their core, diffusion models involve two processes, a fixed forward process that adds noise and a learned reverse process that removes it. This tutorial will meticulously dissect both. Remarkably, diffusion models and score-based generative models have been mathematically unified. They are two perspectives on the same underlying principle, offering complementary insights. Diffusion models offer unparalleled generative quality and diversity. Their training is notably stable, and they inherently cover the full data distribution, addressing issues faced by prior generative architectures. From stunning image and video synthesis to medical imaging and beyond, diffusion models are profoundly reshaping generative AI. Ongoing research continues to push their capabilities, promising an exciting future. The forward diffusion process is a predetermined Markov chain. It incrementally adds Gaussian noise to an image over a finite number of steps, gradually transforming it into pure random noise. Crucially, this forward process is non-trainable. Its parameters, specifically the noise schedule, are fixed beforehand. This ensures a consistent and controlled degradation pathway. At each time step t, we add a small amount of Gaussian noise controlled by a variance parameter beta t. This creates a sequence x0, x1, up to xt, where xt is pure noise. The sequence of beta t values, the noise schedule, dictates how much noise is added at each step. It typically increases over time, making later steps noisier. This is critical for controlling the diffusion. We can directly sample xt from x0 at any time step t. This is possible due to the additive nature of Gaussian noise and simplifies the training data generation significantly. The main objective of the forward process is to generate vast amounts of training data, pairs of a noisy image, xt, and the pure noise, epsilon, that was added to create it.